A graph is a collection of abstract objects called vertices that are joined together by another collection of abstract objects called edges. Some of the graphs can be drawn in a plane so that their edges do not intersect. Others cannot. The first type will be called a planar graph, the former non-planar graph. Let us concentrate on a simple graph, like this one. If, for any two vertices, we'll be able to find a sequence of vertices and edges joining them, namely a path joining them, then the graph will be called connected. If, on the other hand, for a certain graph, like this one, we'll be able to find two vertices that cannot be connected by a path, then the graph will be called disconnected. In what follows, we'll consider only the graphs that are connected. There are some special types of paths in certain graphs in which we can walk in the cycles. Those paths will be called cycles in graphs. In what follows, we'll consider graphs that do not contain cycles. A graph that is connected and do not contain a cycle is called a tree. Consider the resemblance of this structure to a real tree that we see. Let us consider a simpler one, like a tree over here. Let us think how many paths of different length are there in this tree. Let us start from the paths of length 0. Clearly, every vertex of our tree is by itself a path of a length 0, and therefore, since we have 5 vertices, we'll have 5 paths of the length 0. How about paths of the length 1? Every edge of our graph is by itself a path of the length 1, and since we have 4 edges in our graph, we also have 4 paths of the length 1. Okay, that was easy. What about paths of the length 2? Let's count them together. Here's the first, the second, the third, the fourth, the fifth, and the sixth. It's quite easy to convince yourself that there are no more paths of the length 2, and therefore we have 6 paths of the length 2 in the considered graph. Now, what about the paths of the length 3 or higher? If you look at this graph for a second, you shall be able to see that from the central graph we can reach every other vertex. It's easy to conclude from this fact that there cannot be paths of the length 3 or more in this considered graph. So what we have over here, the sequence of numbers 5, 4, 6, 0, is what we call a characteristic vector of the tree of our graph. Imagine right now that we forget our graph. What is remain is its characteristic vector. Can we then, or can we not, recover the tree back? And if we can, how can we do that? If you want to know the answers to these questions, please consider playing the game of trees. Thank you and enjoy.